This physics problem involves concepts of friction, potential energy, and kinetic energy. And friction comes in through its work to remove energy from a system. We're dealing here with a roller coaster. Kim is in a single car on this roller coaster, and the mass of the car in Kim is 800 kilograms. We have a motor mechanism that's pulling the car to the top of the first hill, and that's 47 meters above the ground. At this time, the car is not at rest. It's moving at 2 meters per second, going across the top of the hill. There's a valley then after the first hill, and then there's a second hill that's 40 meters above the ground. We're told that friction in the system is going to take away 5,000 joules of energy as the car goes from the top of the first hill to the bottom of the first hill. And as the car continues on the ride and goes up the second hill, it's going to lose 4,600 joules because of the work done by friction. So we want to do a couple of calculations here. We want to know the speed of the car in Kim at the bottom of the first hill, and we want to calculate the speed of Kim and the car at the top of the second hill. We're going to use two methods to calculate this speed at the top of the second hill. So you should read through problems and then create a sketch that contains the useful information. So my dark line here is the track of the roller coaster. It's going to be a little bumpy ride, but that doesn't matter. It doesn't matter what the shape of the track is between the top of the first hill and the bottom of the valley after the first hill, and then up to the top of the second hill. Energy concepts deal with locations, so you do need to be clear on the location. So I'm going to call location 1 the top of the first hill, and we have information 2 meters per second going across there, 47 meters above the ground as our reference level. And then location 2, I want to know what the speed is at the valley here, and that's 3 meters above the ground, and that has an unknown kinetic energy right now. We want to calculate the velocity. So we're going to conserve energy, accounting for friction. We have a supply of energy here, the kinetic and potential energy at the top of the first hill. The work done by friction is going to remove some of that supply, and then what's left over is kinetic and potential energy at the valley, at the bottom of the hill, after we've gone across hill number 1. So we know the way to calculate kinetic energy is 1/2 mv squared. We know potential energy in a situation with small vertical distance traveled. We can do mgh for the gravitational potential energy. So we put in our numbers. At location 1, the car's mass is 800 kilograms. It's 2 meters per second. Don't forget to square that velocity. The potential energy at the top of hill 1 is the mass of the car, 800 kilograms, the car plus Kim, and then acceleration due to gravity, the g, and then 47 meters above the ground. It is important to know where your 0 point is for the potential energy. I'm selecting here at ground level to be 0 meters. So work of friction takes away supply of energy. We're left at the bottom of the hill, at the valley, 1/2 mv squared. The velocity at the bottom is our unknown. And then mgh, we're 3 meters above the ground at the bottom of the hill. So we continue on. I've just copied that equation to start with here. Now, you should pause and do these calculations on your own calculator. 1/2 mv squared, 1,600 joules. The mgh is a big number, 368,856 joules. And I don't round off in intermediate calculations. I'll wait till the very end to round to 3 significant figures. We're losing 5,000 joules due to the work done by friction. 1/2 mv squared, the 1/2 m is 400 kilograms. And then the potential energy a lot smaller at the bottom of the hill, only 3 meters above ground level, so 23,544 joules. If you do the additions, do the subtractions, subtract this number from both sides, we come up with 341,912 equals 400 times v squared. Divide both sides by 400, and I'm rounding off a little bit here, 854.8 equals v squared. A square root reveals 29.24, and I'll round to 3 significant figures as I work physics problems typically, unless the problem asks me to change that in some way. So 29.2 meters per second, that's in the 50 mile an hour range, beyond, maybe 60 miles an hour. I didn't do it, but divide here by 0.442 meters per second is 1 mile per hour. But considerable speed. It's a fun ride. So part B, we want to calculate the speed at the top of the second hill. So just repeating some information here. And again, in our sketch, now I'm going to do the first method here using the top of hill number 1 as location 1 and the top of hill number 2 as location 2. That'll be the first method that I do the calculation for. So again, we see 1/2 mv squared mgh at the top of hill 1. We're losing 5,000 joules to the bottom, but our location 2 is at the top of the second hill, so we must not forget to remove the energy done by the work of friction going to the top of hill number 2. So there's a second subtraction. And then 1/2 mv squared at the top of hill 2. And at the top of hill 2, we're no longer 3 meters above the ground. We're 40 meters above the ground for the location we're interested in. So you might want to pause and do your calculation to see if you agree with my numbers here. Just continuing copying this result of the calculation. Again, do the additions, subtract 313,920 from both sides, and then divide by 400. I get 117.34 as v squared. And I come up with 10.83 rounded to 10.8 meters per second at the top of the second hill. Is there some reason to say this might be at least plausible? 10.8 meters per second at the top of the second hill. Well, at the top of the second hill, the energy supply we had at the bottom, we've lost some more due to friction. And if you take a look at the velocity, the speed, at the bottom of the hill number 1 from our previous calculation, I'm going to back up a slide here. So we had 29.2 meters per second at the bottom of the hill number 1. Going up to the top of hill number 2, we're down to 10.8 meters per second. It is reasonable that our speed is slower. When I get to the top of hill number 2, some of the energy supply has gone back into potential energy, and we've lost some to friction, so we have less available for the kinetic energy, and a slower speed is plausible. What is the second method that we could use? This first method, location 1, was at the top of the first hill. Location 2 is top of the second hill. The second method, I'm going to make location 1 the valley at the bottom of hill number 1. I'm going to take that as location 1, and location 2 still where we want to know the speed, top of the second hill. And now 1/2 mv squared, my v is at the bottom of hill number 1. It's not 2 meters per second. That was at the top of hill number 1. And the mgh, it's only 3 meters above the ground for location 1, not 47 meters. And we are only considering the motion from bottom here of the hill to the top of hill 2. So we don't subtract the 5,000 joules again. That was energy lost on the way down to location 1. And 1/2 mv squared, mgh, calculate those terms, and I'll copy that to my next slide here. Again, combine the numbers, the joules on the left side. I get 47,015 equals 400. That's 1/2 of the mass, 1/2 of 800 kilograms, and v squared. Divide by 400 and take a square root of 117.54. Round off, I get 10.8 meters per second at the top of the second hill. And if I back up to my first method, I had 10.8 meters per second. Slightly different at the fourth digit, if you notice. and that's due to the rounding off that we've had at the velocity of the bottom of hill number 1, but close enough. It's 10.8 meters per second. It agrees with the first method. So I've got many more sample problems and short lectures for physics and astronomy. I have a simple website, gpclements.com. At this website, you'll find an annotated list of my YouTube videos. In the annotation, I've got the title of the video, how many minutes long it is, a description of the video, and probably most useful, there's a direct link to the YouTube video. You don't have to go back to YouTube and search for the video that you're interested in. These are all organized by topics. Everything here is free. You're not allowed to resell it, but it's all free. You don't give me any information. I don't want your name or email address or anything. And the website does not put cookies onto your computer. Keep working physics problems and ask your instructor if you have questions.